Hi, good afternoon, everyone. So, today's we are in the 11th week of live sessions. Before starting today's classes, I am introduce myself. I am Puvir Maiti, teaching assistant of this course. The course name is Polymer Concept Properties, Uses and Sustainability. Course instructor was Professor Abhijit P. Deshpande. So, I am PMRF student in the Aizen Mohali. So earlier classes we have talked about that polymer and we talk about the polymer synthesis, polymer characterizations, all of this. Today's classes we are mainly focusing on the some question answer session which is coming in your GATE exam, and we also learn about some special polymerization like how we get a syndotactic polypropylene or isotactic polypropylene. So, so before I start, so Ziegler-Natta catalyst. So you know the Ziegler-Natta catalysts are also known as Ziegler-Natta initiators or Ziegler-Natta catalyst systems are a class of catalysts used in production of various types of polymer, particularly polyethylene, polypropylene. They are named after German chemist Carl Ziegler and Italian chemist Giulio Natta, who independently contributed development of this catalyst in 1950. So before start this Ziegler-Natta catalyst, so I am talk about that why we are need this catalyst. So when you are talking about that isotactic polypropylene, isotactic polyethylene. So isotactic means so there your this the polypropylene group where one methyl is present and this that chain. So how this arrangement of this methyl group? Does this methyl group along the polymer chain are arranged in the single one-sided, or it will be arranged is alternatively one side to another side, or it will be arranged like this abnormally like this. So so what important the arrangement? Because this arrangement are also needed in the properties, because all of these properties depend on your molecular structure, and your structure also out tell about that how this material is look like this. When you talk about isotactic or syndotactic polypropylene, so the crystallinity of this material are is high as compared to the atactic polypropylene, and that the crystallinity high is because for the syndotactic or isotactic cases, due to this arrangement they are closely packed into the crystal. So if they are closely packed, so the crystallinity will be high. For the atactic cases, maybe this amorphous. Also, the thermal property of this polymer are different. When there will be high crystallinity, this have the higher melting point or higher TGR, and when there will be low low crystallinity, so this have the lower melting point. So if you want to know that that we can get the polypropylene which have the isotactic and syndotactic one, then the question asks about that how we can get this isotactic or syndotactic polypropylene. So there is the method that developed by the Carl Ziegler and Italian chemist Giulio Natta in 1950. So they have used some transition metal catalyst which are initiate the polymerization, and these catalysts are throughout the reactions will help to get that isotactic and syndotactic polypropylene. So Ziegler-Natta catalysts are typically transition metal compound, most commonly used are titanium, zirconium or vanadium, and often used in the combination of the organo-aluminum compound. So there will be two metal compound at present. One is that titanium, zirconium and vanadium in between one, and another is organolithium, organo-aluminum compound or alkyl aluminum compound. This catalyst enable control polymerizations of olefin, which are hydrocarbons which a double bond between two carbon atoms to the long chain of the polymer. So when we are talk about the double bond into the double bond monomer, and so then we are talk about that free radical polymerizations, and when there will be double bond, so there will be they can be also polymerized by this Ziegler-Natta catalyst. The use of Ziegler-Natta catalyst allows to for the production of polymers with specific properties including molecular weight, crystallinity, and other characteristics. The polymerization process is highly stereoselective, and meaning it can control the arrangement of the side groups and the toxicity of the polymer chain. So the catalyst is like titanium TiCl4, aluminum ethyl chloride, LET2 whole 3, etc. So how the reaction kinetics is look like for the Ziegler-Natta catalyst. So first what will happen is the your metal complex is between the titanium and aluminum, and then this is the vacant site, this is the pi acceptor. So this is the vacant side of the titanium, so this pi electron will be go there. So if this pi electron is go there, so they are forming bond with this. So now what will happen, this CH2 and CH2, so they can form the bond with this R, and this aluminum will be eliminated. So now this Al, and then we get the perfectly bond with CH2 CH2R. So then another CH2 CH2 will coming, and again this process are continuously going on. So this will coming here, and this will be goes out. Sorry. Like this, then another ethylene linkage is coming on, and it will be going on. So how to we get the isotactic one? So what will happen, if there will be CH3 group is present here, so what will happen, so they will avoid the most crowding place. So so CH3 will be always in this side, and it will be always going to a one side, so we can get a isotactic polypropylene. So you have to remember the what type of metal complex we are is a titanium, vanadium, zirconium type metal complex with aluminum Et2Cl, and then your pi acceptor, there will be vacant site created in their titanium. Then your this pi double bond which have the pi electron cloud will give this electron to the titanium, they making a bond. Then due to the steric hindrance, this CH2 is less steric crowding, so aluminum will attack here and R will be replaced, so it will be going on. Then another linkage is coming, and it will be going on. So now the another technique process I am talking about, the ATRP. ATRP means the atom transfer radical polymerization. So what is the atom transfer radical polymerization? So it is a technique like a living polymerization technique. Why we need the living polymerization technique? So all you know that with the kinetics of the polymerization for the addition case and condensation cases will be like this. For addition cases at a very lower conversion, so it will be conversion at very lower conversion, the molecular weight increases. So at very lower conversion, at the molecular weight increases so fast that we cannot control the molecular weight of this polymer. So what we'll do, Uh, also if you go the condensation polymerization, and condensation polymerization will be like this. It will be at the last time it will be increase the molecular weight at 80 to 90% conversion. So what will if you get a polymers like this which have the constant molecular weight increases with the conversion. So this the technique for the living polymerization. There will be various process of living polymerization like ATRP, atom transfer radical polymerization, NMP, and also that ring opening polymerizations. So how this ATRP look like? This ATRP mechanism are given by ATRP chrysosome method scheme. So how what will happen in the ATRP polymerization? So ATRP polymerization we have used that one metal ligand, and another will be that ethyl chloride or ethyl halide, that allyl halide compound. So allyl halide compound, what will happen? So this is the metal. So metal have that probability that take one electron. So if you take one electron from this r dot, from this bond, so it will be r dot. So this will be homolytic cleavage, like I see this. When you talk about one bond, there will be two electron involved into one bond, and when you are doing the homolytic cleavage, the one electron coming here the metal. So metal charges will be, so when it will be cleavage like this, r dot and x dot. So what will happen? Cx dot, the metal will take another electron, so they are bond between this, and their r dot will be remain like this. So then this what will happen, that monomer, again another monomer will come like that. So if the monomer comes, so we are getting the active radical, active polymer radical. So then the active polymer radical, equilibrium with the dormant species, where the active and dormant species are in the equilibrium, and equilibrium in the towards the dormant species is high. So for the normal radical polymerization, there will be no equilibrium between the termination reaction, but here the equilibrium between the active and dormant species. So if there will be equilibrium between the active and dormant species, so we can not get a active polymer radical into the polymerization system high. So if there will be lower active polymer radical, so the chances of reaction as in the addition polymerization will be fast, it will be slower this time. So now we get a polymers like what we want, and we can get the polymers with a particular molecular weight. So for the living polymerizations, it will be the most important steps is the equilibrium between this active and dormant species. Then the propagation is going on, active monomer radical is coming out, then at the termination reactions, so there will be termination by combination and termination by disproportionation. So for that ATRP polymerizations, one thing we have to remember, that the lower disproportionation and termination. ATRP minimize chain termination and the disproportionation reactions which are common in the free radical polymerization. So if you compare the normal free radical polymerizations and ATRP polymerization, for the ATRP there will be minimizes the chain termination and disproportionation reactions which are common in the free radical polymerization. So ATRP are the equilibrium between the active and dormant species. So the two things we have to remember. One is that ATRP minimizes the termination and disproportionation. Second one, the ATRP have the equilibrium between the active and dormant species in the polymer chain is maintained by the reversible nature of the ATRP process. This equilibrium helps to reduce the termination reactions and allows a longer and more controlled chain growth. Next, we talk about the interfacial polymerization. So interfacial polymerization a technique. So like a solution polymerization technique where you used earlier classes I am talking about solution, bulk polymerization, emulsion polymerization, and suspension polymerizations, and we talk about that solution polymerization had the disadvantage due to that solubility problem, and due to the solubility problem of the high molecular weight polymers, and due to this the polymers become with increasing molecular weight the polymers become more sluggish, that is the polymer reaction rate will be slow and we cannot get at the higher molecular weight due to the viscosity of the polymer increases with the molecular weight. So there will be another technique, that is the interfacial polymerizations, where we can get a higher molecular weight. So how this will be technique like? So interfacial polymerization is the chemical process involves synthesis of the polymer at the interface between the two miscible phases. So where here we take the two miscible solution, like solution polymerization we take only one solvent. Here we can take the two solvent and those two are immiscible each other, so there will be interface, and we are taking the two monomers where the two monomers are in the different different solvent, soluble in the different solvent, and these two monomer only can polymerize into the interface, and from the interface we can collect the polymer and we get a higher polymer molecular weight. So typically a liquid or liquid solid surface, this method is commonly used to the produce a polymer with specific properties and applications such as membrane coating and nanoparticles. The interfacial polymerization process typically involves the following step. First is the selection of monomers. The two reactive monomers are chosen typically in each of the immiscible phases. These monomers should be completely and able to react with each other. So monomers should be completely react with each other, but they need to solubilize in the different solvent. The emulsion or immobilization, the two immiscible phases are brought into contact either by emulsification like polymerizations or by mobilizing one phase on the solid substrate for the liquid solids interface. The case of the liquid-liquid interface, the emulsifying agent is often used to create a stable dispersion in the two phases like we are doing in the emulsion polymerization. Then reaction initiation, the reaction is initiated by introducing a suitable catalyst or initiator into the one phases. This catalyst initiator of the polymerization reaction. The polymerization reaction, the monomers at the interface to react to forming the polymer chain. The polymerization reactions occur at the interface leading to the growth of the polymer chains that extend into both phases. Formation of the polymer and film or particles as polymerization proceeds of the solid polymer film particles are formed at the interface. The properties of the resulting polymer depend on the choice of the monomers and reaction condition. Separation and purification. After polymerization is complete, the polymer's product is separated from the reaction medium and typically by filtration or centrifugation. The resulting polymers may require a purification to remove any unreacted monomers or impurities. So interfacial polymerization, you have to remember that polymerization will take place at the interface. Due to this, we can take the polymer easily and they are not, we remove that viscosity problem what will happen in the solution polymerization. So like this one phase and two phases are not soluble like water and you are taking any organic solvent. So these are the interface layer where the polymerization take place. So like interfacial polymerizations happen in the nylon. So for the nylon 6s we are taking hexaminoyl chloride and hexane 1,6 diamine. So adipodyl chloride or hexane diamine. So what will happen? So this is the interface where the polymerization take place and nylon 6 is, and above is the aqueous layer, the lower is the aqueous layer and above this is the hexane layer, and this aqueous, or we can take aqueous layer and organic layer, and there will be polymer from in the interface. Then we collect this polymer into a stirrer and we collect it from here. So this is the very good technique to getting a polymer, which so that you know that when I talk about the emulsion polymerization techniques, so these are free radical polymerization technique, But this interfacial polymerization can also done in the free radical or condensation polymerization. Like this technique is a condensation polymerization technique where the two functional group are involved, amine and acetyl chloride. Now we solve some problem. So the first question was this question are coming in the GATE exam. So lipase is the natural enzyme so it cleaves the carboxylic ester bond among the given. Identify the polymers degraded by the lipase. So lipase only can degrade the carboxylic ester bond. So you have to answer the question. We have to know about this, that what is the uh, mm, what is the structural unit present in the polypropylene, polycaprolactone, PBDF and PET. And if you know the structural unit, we have to find that where the ester bond are present. And if you know the ester bond are present, then we can tell that the lipase is enzyme is used for this. So polypropylene, the polymer will be like this. There will be involved with the methyl CH2CH2. So these are, there will be no like functional group are present. Polycaprolactone, that's like this nylon 6 where the only the amide bond are present, CONH. So these are also not your answer to get that ester bond. So this bond are the amide bond, CONH bond. Next is the PBDA, polyvinyl difluoride. So polyvinyl difluoride will be like this. So there will be fluoride unit is present, so ethylene hydrogen is replaced by fluorine. So also here will be no functional group involved where we can get the ester linkage. So now the last option is remain the polyethylene terephthalate. So you know the polyethylene terephthalate where there will be where there is that ester linkage are present. So when there will be ester linkage are present into the polymer, so there can will be that lipase enzyme will be react. So these are not the correct answer. So the correct answer will be polyethylene terephthalate. And the next question was the polymers with the minimum number of branches. So now I talk about LLDP, LDP. So these all are polyethylene polymer. So but the various types. So polyethylene polymer, that is the LDP, the linear density polyethylene, which have the higher branches. LLDP, which have the lower branches. But HDP is the minimum branches between all of this polymer. So the right answer will be HDP, and the crystallinity of this HDP will be very high as compared to this all of this polymer, because this have the lower branching, and because this lower branching they can easily packed into the easily packed, so they will be higher crystallinity and higher melting point. So now we have to talk about the aramid. So aramid is nothing about a polyamide, and these polyamides are aromatic polyamide like Kevlar. All of these are polyaramid. So the answer will be polyamide, but these are aromatic polyamides. So polyether, polyester, polyamide are not the right answer. A miscible blend is 1:1 composition is formed with. So when you talk about the miscible blend, so miscible blend would be like this, when there will be a similar type of functional group are present into the in your monomer, into a monomer or polymer structure. So polystyrene or polybutadiene. So polystyrene, there will be benzene group present into the structure. You know the structure of the polystyrene will be like this, and polybutadiene. So there will be only involvement only of this. like this polymer. So polystyrene polybutadiene is not a 1:1 miscible blend. So miscible blend polystyrene methyl methacrylate also not miscible blend because they are not any benzene group are present into this structure. These all of them are also not the right answer. Polydimethyl siloxane. These are also not right answer. The only the answer will be the polystyrene and phenylene, because this phenylene group and styrene group both have the benzene. So because of this group, so they will be showing miscible blend into one another. Now you have to talk about the dichemical peroxide. You know that peroxide are as the cross-linking agent. Peroxide and carbon are all are peroxide, sulfur, all are cross-linking agent. Plasticizer like phthalate, all of the plasticizer agent. Mold resistant like stearate, zinc stearate, stearic acid, etc. The change in the stress of the polymer as a function of time at a fixed strain is known as creep. Creep is that while we take a constant load but strain is increased. Stress relaxation. So you have maintained the constant strain, but the your stress will be changes. So the right answer will be stress relaxation. Now you have to match the polymers in the column A with their corresponding polymerization methods in column B. So these are the bisphenol A polycarbonate. So you know the polycarbonate, there will be bisphenol A and carbonyl chloride which are giving the polycarbonate. So it is a step growth polymers and two functional group are involved. When we talk about the polyethylene, so polyethylene there will be double bond. When there will be double bond, so these are all polystyrene butadiene. So polystyrene butadiene can we take by cationic polymerizations. Polyethylene will be your coordination polymerization like MAO catalyst or Ziegler-Natta catalyst. We can take by the polyethylene, and butyl rubber will be your cationic polymerizations. Sorry, and polystyrene butadiene will be your anionic. So right answer will be bisphenol A P2 Q3, that is that polyethylene coordination polymerizations are 4 like anionic polymerization, polystyrene butadiene, and butyl rubber will be your cationic polymerization. So the right answer will be this one, C. Now we have to match the appropriate processing technique in a column A and fabricate of the product. So like the blow molding. So blow molding is the only the process extrusion blow molding or injection blow molding to making the plastic bottle like thumbs up bottle, all of this. Rotational molding, calendering. So calendering will be that taken the sheet. So the P will be 4. So in between C and D and Q. So now this the calendering S2. So this will be your right answer. And R will be injection molding. We can take that plastic buckets, and from rotational molding we can get the basketball. Match the appropriate characterization technique in a column A to determine the polymer attributes to a column. So you know about the gel permeation chromatography. I also talk about gel permeation chromatography is a polymer a technique where we can get the molecular weight of the polymer. So from the gel permeation chromatography we can get the molecular weight. Now the next one is that FTIR. So FTIR spectroscopy are involved in the functional group. X-ray diffraction is the study about that crystal structure, and diffraction scaling calorimetry is the glass transition temperature. So the right answer will be P4, the last one, P4 Q1 R3 that is the difference calorimetry DSC for the glass transition temperature, and X-ray diffraction for the crystal structure analysis. Next question, match each additives in column A with the function given in a column B. Like, so you know dicumyl phthalate is a agent as a plasticizer. Benzoyl peroxide is a curing agent, you also know. Then between the azidoformaldehyde and benzotriazole, hydroxyphenyl benzotriazole is a UV stabilizer. So there will be hydroxy phenyl group. So those are UV stabilizers. So azidoformaldehyde is your blowing agent. So there will be formaldehyde, that is that nitrogen will be coming out from there, formamide. So this will be connected as a blowing agent. So the right answer will be P3, Q4, R1 curing agent, and S2. Plot the stress against the shear rate for various types of fluid in the given. PQRS, you know. So when there will be straight line, so this will be the Newtonian type of behavior. So Newtonian type of behavior in between these two. So when there will be like this will be after some stress, your materials will be like a Newtonian type. So then it's called Bingham plastic. So the right answer should be this. Now the pseudoplastic and dilatant. Between the pseudoplastic, you note pseudoplastic with increasing shear stress, your shear rate will be decreases, and dilatant with increasing shear stress, shear stress, your shear with increasing shear stress, your shear rate will be increases. So the right answer will be this, B. Which of the following as an elastomer? The polyamides are not the elastomer. Vulcanized polybutadiene should be the elastomer. Polyethylene terephthalate not the elastomer. High density polyethylene is a thermoplastic, not the elastomer. So these are thermoplastic, polyethylene terephthalate, polyamide plastic material, but vulcanized polybutadiene are only the elastomer material. Elastomer material because we have the need the lower stress to maximum strain we can get. Which of the following is an example of biodegradable polymers? So biodegradable polymers need a biodegradation unit like the lactite is a biodegradable polymer. Polypropylene, when there will be only hydrocarbon, they never be the biodegradable. When there will be carbonyl or oxygen unit are present, so they may be the biodegradable. So polyamide is not biodegradable. Polyethylene also not biodegradable. The right answer will be polylactite is the biodegradable polymer. Now you have to match the following multiple choice question. The 2 marks is of the following. So the match between this, the tripholyl phosphate. So when they talk phosphate, so phosphate are the plasticizer. Then trioxyvinylsilane, azidoisobutyryl, and phenol. So phenol are in the antioxidant. So and your blowing agent is isobutynitrile and triethoxyvinylsilane. So triethoxyvinylsilane may be the coupling agent and this will be a blowing agent. So right answer should be P3, P3Q1. This will be a right answer. This is not the right answer A. C also not the right answer. D also not the right answer. So only B the right answer. So up to this today's classes, up to this, so you have I have again what we have learned today. So today's class we have talked about the Ziegler-Natta catalyst. So Ziegler-Natta catalyst is used to get a isotactic or stereospecific polymers, and why you need this stereospecific polymers. So stereospecific polymers are needed for a particular application. We are getting a syndrotactic or isotactic polypropylene. Why this syndrotactic isotactic polypropylene are needed? Because they have the particular sharp melting point as compared to the atactic polymer. So what are the catalyst system? Like this catalyst system add a titanium, zirconium or vanadium based chloride with the aluminum ethyl or organoaluminum compound. How this catalyst reaction is going on? Like when there will be a titanium and aluminum metal complex as formed, there will be vacant site created into the titanium metal. So when there will be vacant site, then now the chance of this pi acceptor will be give the electron into the vacant site and make a bond between this. Then now the aluminum will be attack this CH2 side and R will be R bond will be cleavage, and we are getting like this. So then another ethylene or another propylene units comes into there, and we can get a isotactic or syntactic polyethylene or polypropylene. Then we talk about the living polymerization technique. Living polymerization, in between the living polymerization technique, the ATRP is a technique where we can get the living polymer with the desired molecular weight. When we talk about the addition or condensation polymerization, we cannot get a desired polymer weight because this have that um, difference in the kinetics. So if when we control the kinetics, we have to go a particular synthetic technique, which is the ATRP mechanism, atom transfer radical polymerizations. We have developed by the Kirchhoff methodology, where we take a metal ligand, we take an electron from that a alkyl halide, and they are from that radical. Then this radical the attack the monomers, and monomer active polymer radical, and there will be a equilibrium between the active polymer radical and the dormant species. So this active and dormant species equilibrium and the equilibrium morely shifted to the dormant species are very important in the ATRP polymerization. So for the ATRP polymerization, two things we have to remember. One is the minimizes the chain termination, and the second is the equilibrium between the active and dormant species. Then we will talk about the interfacial polymerizations. For the interfacial polymerization, we will talk about the solution polymerizations that are not suitable when we are getting the higher molecular weight, because due to the high increase of the viscosity. So interfacial polymerization technique is the technique where the two liquid which are invisible to each other, and the your polymerization take place into the surface, like an emulsion polymerization technique where we take the emulsifier and we have formed the micelle and monomer doublet, and the polymerization will take place into the micelle. So like interfacial polymerization, the polymerization only take place into the interface. Like this is the technique for the to get the nylon 6,6. So where the interfacial, so this is the picture where the interfacial polymerization, the polymers nylon 6s are synthesized in the interface, so between the organic and aqueous layer. So we take out the polymers by a rod. Then we solve some problems like the lipase. Lipase, we have the enzyme which degrade the carboxylate. So carboxylate only polyethylene terephthalate at the ester bond. So it will be degrade this polyethylene terephthalate. Then we talk the branches. In the branches, there will be high density polyethylene of the lower number of branches as compared to all of this, because high density polyethylene higher crystallinity and the low branches. Aramid is the polyaromatic polyaromatic amide like this Kepler, which have the higher strength applications, are also called the engineering plastic also. A miscible blend. So to when I talk about the miscible blend, there will be some similar monomer unit present into the both of the polymers, like polystyrene polypropylene oxide have the both of similar benzene unit. When I talk about the peroxide or sulfur, all are the curing agent. Plasticizer, like plasticizer is that phthalate, which are the plasticizer. Phosphate, mold release agent like stearic acid, stearate. The changes in script is the when you get a particular constant stress into the material, and your strain will be different, then that will be your creep. The stress relaxation, you maintain the strain and you are getting the different stress, is the stress relaxation. Then we match like bisphenol polycarbonate. Bisphenol A is the condensation polymerization. Polyethylene is the Addition polymerations also it can be synthesized like Ziegler-Natta catalyst, Mao catalyst, like a coordination polymerization. Polystyrene butadiene is the cationic polymerization, is the anionic polymerization technique, and butyl rubber a cationic polymerization technique. Blow molding. So from the blow molding we can get the plastic bottle, thumbs up bottle like this. Injection molding we can get also the bottle or also plastic bucket. All of this calendaring that PV sheet, and from the rotational molding we can get the basketball. Gel permission chromatography technique to get the molecular order of the polymer. FTI spectroscopy to get know about the functional group of the polymers. Differential scanning calorimetry know about that. TG thermal transition of the polymer like TGTM, X diffraction, the crystal structure. You know the crystal structure of the polymer. So dicumyl thiolate as a plasticizer, benzoyl peroxide also as curing agent when there will be hydroxyphenyl that act as a UV stabilizer, and azoformaldehyde as a blowing agent. When we are talking about the Bingham plastic, Bingham plastic is that plastic where that after a certain stage the plastics becomes plastic becomes a Newtonian type, showing a Newtonian type behavior. So these two are the pseudoplastic dilatant, which are the non-Newtonian type behavior. For the pseudoplastic, after shear stress is decreases with shear rate, and but for the dilatant one, with increasing shear rate, shear stress, the shear rate is increases. Then the elastomer, so vulcanized polybutadiene is the elastomer. Which of the following example of the biodegradable polymer? So polylactide is the biodegradable polymer. Then we talk about that similar like blowing agent. So blowing agent as isobutyl nitrile phenol with the antioxidant. When there will be phenol or hydroxyphenol, all of these that antioxidant. When there will be phosphate, so phosphate are plasticizer, and when there will be silane, so there will be various type like into a one polymer, so they can be act as a coupling agent. So up to this, thanks for joining. So now I stop the today's classes.